Okay, we'll talk about reinforced concrete beam mechanics now, because again, the general beam mechanics dealt with a beam that was this perfect beam, all one material, blah 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 blah. You know, reinforced concrete isn't this perfect beam. It's made up of two materials that are drastically different from one another. You know, steel, very good in tension. Concrete, very good in compression, but really not that good in tension. So, what's going to happen with a concrete beam? Well, we'll sort of draw that cross section that was up there for the general review of beam mechanics, and sort of, but this time here's this, my layer of steel that's down in the tension side. But one thing that's going to be different, the neutral axis in this perfect homogeneous beam that we looked at back in strength of materials, the neutral axis was right at the center, or right at the centroid of the shape. Okay? In this case, that's not really the case, because I got two different materials. This material having a very drastic increase in modulus of elasticity. So the neutral axis really is going to be probably closer to the top. But there's still a neutral axis. Okay? The other thing that makes this different in a reinforced concrete beam is the concrete that's on, in this case, below the neutral axis is going to be in what? So it's going to be in tension. The problem is, as soon as concrete comes under any substantial tension, what happens to the concrete? It cracks. So this is sort of interesting. If the moments are very, very low, the reinforced concrete beam behaves almost like we thought of back in strength of materials. It behaves like elastically. But as soon as the moments get any size at all, the concrete begins to crack. In the strength design philosophy, we neglect the tensile capacity of all concrete. So basically you could be looking at this beam, and in our way of looking at things, since we are designing for largest capacity, we're not designing a capacity that's only a quarter of the way to what it can hold. We're designing a capacity that's, the maximum design capacity. We're going to assume all this concrete just doesn't do anything for strength-wise because it's cracked. So the only thing that does anything for us strength-wise in tension is the steel. So my tension force is going to be down here in the steel. It's going to be located at the centroid of the steel, or the layer of the steel. All right? What happens in compression? Well, concrete's good in compression, but because it's a different type of setup here, the distribution in compression of stress is actually a parabolic distribution. Now, how many people know the formula for the area of a parabolic shape? That's what the ACI thought. ACI thought, man, early in the morning, asking people about parabola is probably a bad deal. So what they do is if I change that question around, I said, hey, what's the area of a rectangular shape? Would you be able to get that one? Okay, that's what the ACI thought too. So instead of using really what it is, probably a parabolic distribution, the ACI uses a rectangular approximation of stress. Some people call this the Whitney stress block. But as far as that parabola goes, we just sort of say goodbye to it. So they're going to say, hey, up in compression side of the beam, we're going to have a rectangular, or assume a rectangular distribution of stress. Now that doesn't come all the way down to the neutral axis, okay, and they can estimate how far it goes down relative to the strength of the concrete, but we call this depth of the block here of compression stress, we call that A. So there's some more notation for you. The stress, since we're looking at sort of a maximum stress, you know, how much can the concrete beam, you know, come up, you know, take as it comes up to its maximum capacity. The stress that we can come up to is 0.85 F prime C. Now I know what you're thinking. You say, hey, I thought we were coming all the way up to the capacity of the components, and why isn't that F prime C? Why is it 85% of F prime C? The answer is that's part of the approximation of the rectangle. Remember, we really have a different distribution, but the 0.85 is this approximation that we made. So, if this is my compression block, where would the resultant compression force act? It's rectangular. Where do I put the resultant of a rectangle? The center of the rectangle, right? So, remember back in the general beam mechanics, we had this T force and C force. Hey, I got the T and C force again. It's separated by a distance here. Anybody tell me what that distance is? It's the arm. Give me a value for the arm, or a formula for the arm. What did I call this distance from the compression side down to the steel? Compression side down, D. But it's not D, is it? Because I'm in the middle of the stress block. So what would it be? D minus 1/2 A, or I'll write it as D minus A over 2. So you just derived, basically, the first formula you're going to need for moment capacity of a reinforced concrete beam, nominal moment capacity we call this. Here's the force, T, or you could substitute C there because they're the same. But T times the distance, force times distance, force T, distance D minus A over 2. Okay. And that'd be your moment capacity. Force, maybe the force is in kips or pounds, whatever. Distance, inches, you know, usually. But I mean, if we wanted to take inches, we wanted to divide this by 12, we could put it in the feet. So again, you got, let's say, kips in feet, foot kips. Or maybe this is pounds in feet, foot pounds. If you don't divide it by 12, maybe it's kips and inches, inch kips. So there's your moment, your nominal moment capacity. All right? Okay, questions on that?